This is our third video lecture over section 6.2 using the normal distribution. And in this video, we're going to be looking at a different application of the normal distribution. The first two videos were dedicated to finding probabilities using the bell curve. Now we're going to look at a different kind of problem, and to motivate the idea, let's look at a specific example. It's our favorite variable of the videos. The heights of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Notice the different kind of question here. It doesn't tell us to find a probability. It says find the 90th percentile for this variable. So here we're not being asked to find the likelihood of an event. We're being asked to find a value of the variable given its rank, its percentile. In a sense, that percentile is already an area. If I draw a picture of the scenario here, we know that we've got this bell curve. The mean is 63.6. If there's one thing you're going to learn this chapter, it's that the mean height of women is 63.6 inches. I've used it so many times. The standard deviation is 2.5 inches. And now we're being asked to find not a probability, but a percentile, and in particular, the 90th percentile. The 90th percentile would be a value of the variable. It'd be some number on this horizontal axis. And if it's in the 90th percentile, it's going to be bigger than the mean, because the mean is in the middle. It's the 50th percentile in a normal distribution. The 90th percentile, which we denote by p sub 90, would be somewhere over here. What do we know about this percentile? Well, we know the area to the left of it must be 0.9. That's what's going to make it the 90th percentile. The area shaded to the left is 0.9 units, whatever the units are. And the question is, what is p sub 90? What is that 90th percentile? Using normal CDF for this problem isn't the most efficient way to do it. That would be like a guessing game. You'd have to keep guessing this bound until you wind up getting a probability really, really close to 0.9. We don't need to do it that way because the calculator comes with a function specific to this application. If you're trying to find a specific bound given the area, the mean, and the standard deviation, the calculator can do that. And because this is kind of the opposite or the inverse of what we did before, the calculator function is called InvNorm. Consider a normal distribution with mean, mu, and standard deviation sigma. The bound below which the area under the curve is A is given by inverse norm of the area, the mean, and the standard deviation. Now I admit the way that this is worded is kind of weird. The bound below which the area under the curve is A. What does that mean? Well, let me draw you a generic picture here. When we say the bound below which the area is A, we mean given this bound, the area to the left below that x value is A. If we know the area to the left is A, then inverse norm of that area, comma the mean, comma the standard deviation, will give you that bound. It will tell you what the value of the variable has to be in order to capture that much area on the left side. Now, how can we use that? Well, let's go back to the picture for our specific example. We wanted to find the 90th percentile of women's heights, and we know that the area to the left of our bound is 0.9. This is exactly what inverse norm is built to do. We're going to use inverse norm 0.9 because the area to the left of our bound is 0.9, comma 63.6 because the mean is 63.6, comma 2.5. And the calculator's output will be the height at which 90% of the area, 90% of the data, falls below that bound. Just like our other calculator functions, I'm going to have to demonstrate this twice for our first example. Once for those of you that have the input screen and once for those who don't. Let's start with the input screen. Inverse norm is directly below normal CDF. If you push second vars, it's choice 3, inverse norm. You see that this prompts you for the 3 inputs. The one thing this doesn't remind you is that we need the area to the left of our bound. So the 90th percentile is bigger than 90% of the data, so the area to the left would be 0.9. The mean was 63.6. The standard deviation is 2.5. We're going to paste that on the main screen. And then hit enter. And we get an answer of about 66.8. And we don't freak out about getting an answer bigger than 1 because the answer isn't a probability. It's a value of the variable. This is the height of a woman. A woman who's 66.8 inches tall is taller than 90% of all women. 66.8 inches. You can see this is the opposite of what we were doing in the previous two videos. In those videos, we were given a bound or two bounds and we found an area, which we interpreted as a probability. Here we took an area and we found a bound, the exact opposite of what we did before. That's why this calculator function is called inverse norm. Let's demonstrate this without the input screen. Second vars, choice 3 for inverse norm. And you get this inverse norm prompt on your main screen when you don't get the input screen. You just put in the three inputs separated by a comma. You need the amount of area to the left of your bound, then the mean, then the standard deviation, and there's that 66.8 again. So in a sense, you can think of inverse norm as a function that finds percentiles in the normal distribution, but it's more flexible than that because you don't have to find a true percentile. Also, the word problem might not word it as a percentile. Like, let me show you another example. When kept as pets, the lifespan of the American bobtail is a normally distributed variable with a mean of 13 years and a standard deviation of 3 years. Find the age one of these cats must reach to have a lifespan in the top 3%. So let's start with how we know this isn't a normal CDF question. Like, I see that it says it's normally distributed, and in the past when we saw that, we immediately jumped to normal CDF. Why don't we do that here? Well, it's because this question isn't asking for a probability, right? We're looking at the age that you have to reach to be in the top 3%. So that 3% is like the probability that one of these cats lives that long. It's giving us a probability, and it's asking for the bound. It's asking for the age. Before, we were given the bounds, the values of the variable, and we were coming up with the probability. Now we essentially have a probability and we're coming up with the bound. This is the inverse of what we were doing before. So this is an inverse norm question. Let's draw a picture of the scenario. I still think pictures are a good idea here. Normal curve. The mean age of one of these cats, at least in the home, is 13 years. The standard deviation is 3 years. And we're asked to find the age that one of these cats would have to reach to be one of the oldest 3% of all such cats. So if you're in the top 3%, you're somewhere over here. This is the value of the variable. I'm just going to call the variable x. It wasn't worded as a percentile, so I'm not going to use the percentile notation. And it says it's in the top 3%. So if you're in the top 3%, that means only 3% of the area falls to the right. This is 3%, which is 0.03, not 0.3. 0.3 would be 30%. So you can see in the picture that we have an area and we need the bound. This is what inverse norm is built to do, almost. The problem is that inverse norm wants to know the area to the left of your bound. So this minimum number for the top 3% actually divides off the bottom 97% from it. The area to the left is 0.97, and that's what the calculator needs to know. When you go to inverse norm, you always want to input the area to the left of your bound, 0.97, then the mean, then the standard deviation. The calculator is going to give us the bound, the value of x, that divides the bottom 97% from the top 3%. Okay, let's put this into the calculator. Second vars, choice 3. Area to the left of our bound is 0.97. The mean was 13. The standard deviation was 3. Enter. And 18.6. And this is an 18.6%. Remember, the answer is not a probability here. This is a value of the variable. The variable is being measured in years. It's an age of one of these cats. So only 3% of these cats live 18.6 years or longer when they're being kept as a pet. Let's go back through the problem one more time and make sure we understand what was going on and how we identified it as an inverse norm question. So it tells us that it's normally distributed, but it doesn't ask for a probability. It tells us to find the age of one of these cats. And so we're finding a value of the variable, and we're given the area to the right of our bound. We know that the bound cuts off the top 3% of all cats. So we drew the picture, but the area that was given was to the right of our bound, and inverse norm needs the area to the left. So if the area to the right is 0.03, the area to the left would be 0.97. You can also think of that in terms of percentages. 3% was to the right, so 97% is to the left. And then we ran the inverse norm function to get that bound. Notice that our answer is bigger than the mean, which makes sense because it was in the top 3%. If you made the silly mistake of just grabbing the 0.03 from the problem, right? You see the 3%, you're like, oh, that's 0.03. Let me put that into the calculator. Second vars, choice 3, and I'll put in the 0.03 with a mean of 13 and a standard deviation of 3. The answer you get is smaller than the mean. There's no way that's in the top 3%. So if you make that mistake, you should catch it if you take just 1 second to think about whether or not your answer is reasonable. There's no way 7 years is in the top 3% when the mean lifespan of these cats is 13 years. That's just not even reasonable. So you can catch that mistake if you take a moment to make sure that your answer makes sense for the application. And let's look at another one. This one might be a little more interesting because it's about money. The mean starting salary for registered nurses in the United States was $57,000 in 2019. Let's assume these salaries are normally distributed with a standard deviation of 12,000. There's a lot of variation in the salaries for registered nurses depending on the state in which you're working. So they got a pretty large standard deviation. Find the starting salary required to be paid in the top 25% of all registered nurses. So this did not include any overtime pay. That's literally just the salary. But somebody who's interested in the profession is like, well, what would I get paid if I was in the top 25%? Let's see, we're assuming that the variable is normally distributed. So I can draw a picture for the scenario. I've got this bell curve with a mean of 57,000 and a standard deviation of 12,000. And we want to find a starting salary that will land a person in the top 25%. If you're in the top 25%, then you're again larger than the mean. We don't know what this value is, but we know that it divides off the top 25%. So we're looking for this bound given an area, and that's what inverse norm does. So this is inverse norm of 0.25. Nope. That's not right. What mistake are we making? We always have to put in the area to the left. And if you ran this with 0.25 in there, it would give you the bound for the lowest 25%, and that answer would be smaller than the mean, and hopefully you would catch that mistake. But we're not going to make that mistake. We're going to find the area to the left. You can think of it in terms of area. The total area under the curve is 1, so the area to the left must be 0.75. Or you can do it in terms of percentage. If it divides off the top 25%, then it also divides off the bottom 75%. This is essentially the 75th percentile, the third quartile. The order of the inputs is area to the left, which is 0.75, then the mean, which is 57,000, and then the standard deviation, which is 12,000. Okay, let's see how much money this would be. So second vars, choice 3, because we have the area and we're looking for the bound. 0.75, because that's the area to the left of our bound. The mean was 57,000. The standard deviation was 12,000. Enter. And we get an answer around $65,000. If we wanted to round to the nearest dollar, it would be $65,094. But we're saying about 65,000. Notice that that's bigger than the mean, so that makes the answer reasonable. But if you start at $65,000 or more, you're in the top 25%. And I did this for registered nurses, but with a little bit of research, you could do the same thing for whatever your desired profession would be. You might find that interesting. Let's look at one more example. It says the time spent on stage by a certain band is normally distributed with a mean of 126 minutes and a standard deviation of 12 minutes. Find the times on stage that would put a show in the shortest 10% of their gigs. So you've got this band, and when they put on a concert, they're usually on stage for a little more than 2 hours. There's some variation to their show times. The standard deviation is 12 minutes. And we want to find a bound that would divide off the shortest 10% of their performances. What would be considered a short concert for this band? We're told that this variable is normally distributed. We know the mean and the standard deviation, so we can draw a picture. The mean is 126, Standard deviation is 12. And let's go back to the problem. We want to find the time that would be in the shortest 10% of their gigs. So if the show is shorter than average, then that bound is going to be to the left of the mean. And this is one of the reasons I wanted to do one more example. I hadn't demonstrated one where the value of the variable is on the left of the mean, but it certainly could be. So the x value we want is somewhere over here. And if we're talking about one of the shortest 10% of their shows, then we're given the area to the left. That area to the left is 0.1, 10%. There's no reason to switch to the 90% here because that's already the area to the left. We know the area to the left, we know the mean and the standard deviation. This is what inverse norm is built to do. Inverse norm 0.1, 126, 12. We're anticipating getting an answer smaller than the mean this time because it's going to be one of their shorter concerts, so it's something less than the mean. So let's find out what this bound is. Second vars, choice 3. The area to the left is 0.1. The mean is 126. The standard deviation is 12. And again, we expect to get an answer smaller than the mean because this is one of their shorter concerts. It's 110, 111 minutes, I guess, if we round to the nearest minute. You can see that's not much smaller than the mean. It's a little more than a standard deviation away. There was nothing special about this example. I just wanted to demonstrate an example where the bound was on the left side. And I also wanted to do one more example where we did not change the area that we were given. After doing those previous two examples, some people get lulled into a feeling that they always have to switch the percentage that they're given. You only do that if you're given the area to the right. And those kinds of problems are usually worded by saying you're in the top whatever percent. Here it says we're in the shortest 10%, that's the bottom 10%. And in the first example, we were given a percentile. And this is one of the reasons why we had to study the definition of a percentile. A percentile tells you the percentage of data below your bound. So in those two examples, we did not do anything special to our input. We were given the area to the left. And how do I expect you to juggle all of those ideas? I want you to draw the picture. That's why I say you should draw the picture. If you draw the picture, you'll know if you have the area to the left or not, and you can go from there. Okay, that's the end of section 6.2. If you have questions about inverse norm or anything in that section, just get a hold of me.